Day 2 of Module 2, Lesson 1, Topic 1, Activity 1.3, Connecting Constants Difference, Slope, and the Average Rate of Change. In the previous activity, you determined that the constant difference of the chair heights and the slope of the line are both equal to 8 inches per chair. Is the slope of the linear function always the constant difference of the corresponding arithmetic sequence? Consider the graph of the arithmetic sequence represented by the general function f of x equals ax plus b. Identify the constant differences of this sequence in the graph. Complete the table for consecutive values of the input. Term number n, we have f of n, which equals an plus b. Term number n plus 1 is f of n plus 1, which is a n plus 1. We can continue this pattern where we have f of n plus 2 gives us a times n plus 2 plus b. F of n plus 3 gives us a times n plus 3 plus b. Accidentally answered number 2 first, so we completed the table for consecutive values. Now let's look at the graph to answer number 1. Identify the constant difference of the sequence in the graph. So here, on the x value, I'm increasing by 1. For my y value, that's my common difference. I'm increasing by 1 on my x's, and on my y's is my common difference. Same pattern throughout. Let's look at number 3. Select any two consecutive input values in the sequence. Use the expressions for the term values to determine the constant differences in the sequence. If I take any of these two sequences and subtract, let's say that I take the first two. So I'll do a n plus 1 plus b minus a of n plus b. We're going to take this equation and move to a whiteboard to have some more room here. This actually needs to be in parentheses because we're subtracting all of that. The first thing we need to do is distribute in the a, and I'm going to bring it up here. So we've got a n minus a plus b minus all of this. So we could think about distributing in that negative. So that would be a negative an and a negative b. And then what you're going to see is some things canceling out. Our b's are opposite, so they cancel out. Our a of n are opposite, so they cancel out. And I'm left with a. Oops, I made a mistake here. That was supposed to be a plus 1 right there and a plus a there. So that gives me a positive a, which is my slope. We could also think about n being our slope. So that answers number 3. Question number 4. Recall that the slope of the line is constant between any two points on the line, not just consecutive points. Use the table in the graph from question 2 to complete each task. Identify the slope of the function on the graph. We're going to skip over this section. This is just proving the slope formula, and we know that the slope formula works. So we're going to go on to activity 1.4. Verifying that common differences in slopes are the same. Let's look at these three graphs and their explicit formulas. For each graph and arithmetic sequence, complete each task. Identify the constant differences in the explicit formula and on the graph. So here we discovered that for graph A, we have a common difference of -4. For graph B, we have a common difference of 2. And for graph C, we have a common difference of 2 as well. For part B, it says rewrite each explicit formula in functional notation. So if we take an equals 2 minus 4 times n minus 1, and we're going to take an equals -4 plus 2 times n minus 1, and then for graph D, why is it called graph D? Why not graph C? I guess that's graph D. Interesting. A of n equals 4 plus 2 times n minus 1. And I'm going to go back to whiteboard to give us some space here. So we've got graph A, graph B, and graph D. Don't know why it's called graph D. First thing we want to do is distribute in the -4. Notice that's a -4. So that's going to be our f of x. For our functional notation, bring down the 2. -4 times n gives me -4n. -4 times -1 gives me a +4. Combine the 2 and the 4. F of x equals -4n plus 6. And instead of the n, we need to be using x for our functional notation. Or we could use f of n equals -4n plus 6. Then let's take graph B. F of n equals, distribute in the +2, so bring down the -4 plus 2n minus 2. Combine the -4 and the -2, so f of n equals 2n minus 6. And for graph D, f of n equals 4 plus 2n minus 2. F of n equals 2n plus 2. Let's go back to our page. And there's the answers for B in function notation. For graph D, graph B, and graph A. C, it says verify that the constant difference is the same as the slope of the linear function. And it is. Notice that the slope did not change, so yes, it is the same. Part D, it says describe the first term in the explicit formula. Is it related to the y-intercept? So if we think about a1 as our first term and subtracting our common difference, that gives me f of 0. So for graph A, we had 2 as our first term, and we are going to subtract our common difference. And remember, our common difference was -4, and that gives us 6, which is our y-intercept. For graph B, recall that your first term was -4, and if we subtract our common difference as 2, that gives us a y-intercept of -6. So these are your y-intercepts. And then for graph D, our first term was 4. Subtract your common difference, and that gave us 2 as our y-intercept. So just something to analyze there. On the next page, we've got activity 1.5, describing constant sequences. Kenyatta Cat loves to knock over flower pots each morning. She counts the number of flower pots her cat knocked over during the night before. She uprights them again. Sequence C represents the number of flower pots knocked over on day 1, day 2, etc. Determine the constant difference and write an explicit formula to represent sequence C. Then create a table of values and graph it. All right, so my first term, my second term, my third term, my fourth term, and my fifth term all seem to be 3, 3, 3, 3, and 3. So if I graph these as ordered pairs, that would be 1 and 3, 2 and 3, 3 and 3, and 4 and 3, and 5 and 3. So let's see, 1 and 3, 2 and 3, 3 and 3, 4 and 3, 5 and 3. Number 2, use function notation to write an equation representing the relationship between the number of x days and the number of new flower pots. C, interpreted by the function in the context. Didn't completely answer 1. Let's go back to 1 before we go to 2. Determine the constant difference. So if I'm taking the difference of 3 minus 3, that's going to give me 0. That gives me a slope of 0. And write an explicit formula to represent this. So my explicit formula of a(n) would be so if I'm writing my explicit formula, then my first term would be 3 minus my common difference of 0 times n minus 1. And we need to clean this up because 0 times anything cancels out. So you'd really just have a of n equals 3 as your explicit formula. Number 2, use function notation to write an equation represent the relationship between the number of days and the number of new flower pots. C, interpret the function in terms of the context. So here, I'm going to use c of x. C of x equals 3. This is a constant function. The slope is 0. The slope is 0, and the y-intercept is 3. Number 3, prove that the slope of c of x is equal to the common difference of c. So to answer this question, a couple of things that you could look at here. Remember, our sequence was 3, 3, 3, 3, 3, 3. And so we're adding 0 or subtracting 0, however you want to think about it. So the common difference was 0 here. We calculated our slope as also being 0. We did 3 minus 3, which gives us 0. So my slope is 0. My common difference is also 0. Number 4, consider a similar sequence, sequence D, -5, -5, -5, and so forth. Write function d of s to model this sequence. All right, so again, my common difference is going to be 0. So my slope is going to be 0. So d of x equals 0 slope in my first term, which is -5. So d of x equals -5. Number 5, prove d of x is a constant function. The slope of d of x is 0. The values of the dependent variable remain constant over the entire domain. Therefore, you have a constant function. Look down here at the remember. If the values of the dependent variable, which is x, of a function remain constant over the entire domain, then the function is called a constant function. So we have 2 examples of a constant function. D of x equals -5 and c of x that equaled 3. Talk the talk, making it plain and clear. You have proven that all arithmetic sequences can be represented by linear functions. Complete the graphic organizer to summarize the connections between arithmetic sequences and linear functions. Then describe how you can tell a linear relationship exists given a table of values or graph. So here we have the arithmetic sequence broken down. We know that a of n is our term number that we want, and a of n also represents f of x in our linear function. And f of x stands for our output value. D represents our common difference, and here it represents a, our slope, which I find that very odd because typically slope stands for m. So be mindful of that. But that represents our slope or our rate of change. N is the term number that we wanted. Here in linear function notation, we're going to use x. That's our dependent, that's our input value. And a1 minus d is our y-intercept. That's where it crosses the y-axis. Below, you have a graphic organizer that talks about the characteristics and representations of linear functions. Jot down some ideas and brainstorm what we've talked about through this lesson.